Hello, my dear students. Welcome to online classes on design of mission elements. I am Dr. Bharat from Global Academy of Technology. In today's session, we'll be discussing how to solve numericals in this subject. We'll be mainly focusing on numericals on axial, shear as well as bending loads. Before starting the numericals, let us revise the basic formulae in solving these numericals. These are the textbooks which I'll be using throughout this course. Shiegler's Mechanical Engineering Design by McGraw-Hill Publishers, Design of Mission Elements by V.B. Bhandari from McGraw-Hill Publishers, as well as will be exclusively using a mission design data handbook by Lingaya from Summa Publishers. So the data on the formulas are taken from this mission data handbook. This is the table which we'll be making use of while taking the shear, moment and deflection formulas in case of beams. Especially the third column as well as fourth column will be considered while solving the numericals. In the third column, we'll be taking the maximum bending moment, and in the fourth column, we'll be considering the maximum deflection. So this table gives the values for beams subjected to different types of loading and end conditions. Now this table number 2.8 is continued for next 3 pages. You can see here a simply supported beam with uniformly distributed load has also got a maximum bending moment and maximum deflection. These are the formulas which will be making it used in the numericals. Now this table which you see on the screen will be making use of this table to determine the properties of cross sections during bending. Now this table gives the values of section modulus for different cross sections. Also we can see the values of moment of inertia using this table. Note that in this table, for especially in case of rectangular section, cross section, the parameter B or the dimension B is exactly parallel to the axis and the dimension H is perpendicular to the axis. The same notations will be using it while solving the numerical. We will consider B, a dimension B, always parallel to the axis, and the height H or the depth H always perpendicular to the axis. So in this formula BH square by 6, it is clearly said that the parallel dimension multiplied by perpendicular dimension square by 6. Similarly, the similar terms will be used while calculating moment of inertia. So even though if the cross section has changed, now as in this case, since the dimension B is parallel in this case, as well as the H, the perpendicular dimension is always considered as H. The parallel dimension is always considered as B. The table 2.2 from this data handbook is used to calculate polar section modulus, which is given by J by C, where J is the polar moment of inertia and C is the radius of the shaft or the distance from the neutral axis to the extreme fibers. This value is called as C. So students are requested or advised to kindly note this tables. Table 2.2 for finding polar section modulus, table 2.7 to determine section modulus in case of bending stresses, and table 2.8 in finding the maximum bending moment as well as deflection of the beams. With these basics, let us also start the numericals. Let us start the first numerical on axial loading. An SAE 1045 annealed carbon steel having a yield stress of 309.9 megapascals is subjected to a tensile load of 60 kilonewtons. We need to calculate the diameter of the rod using factor of safety of 3. So from the question, it is understood that the carbon steel with 309.9 megapascals yield stress is subjected to tensile load of 60 kilonewtons. So it is understood that there is an axial tensile load of 60 kilonewtons. Also, since he is asking us to find the diameter of the rod, the cross section of the rod is circular. So this will be the probable diagram of this numerical. Let us start working on this numerical by listing the given data. He has given the yield stress 309.9 megapascals. The factor of safety has been given in the numerical as 3. The load is 60 kilonewtons. We need to find the diameter of the rod. Since sigma y is the yield stress which is obtained from standard tensile test, we will be making use of allowable stress in this numerical. The allowable stress sigma y is given as sigma allowable is equal to sigma y by factor of safety. So the allowable stress in this case will be equal to 103.3 megapascals. After finding this allowable stress, let us write the equation for the axial stress. The type of stress in this numerical is axial stress, and the formula sigma A is equal to F by A, force by area. So substituting these values in this numerical, sigma A is 10.3 megapascals, force is 60 into 10 power of 3 newtons, and area is what we need to determine. Based on after finding the area, using this area we'll be finding the diameter. So we have got this area as 580.832 mm square. After finding this area, we'll be using the area of a circle as pi d square by 4. Once we get this area of the circle, substitute the value of A in this equation to determine the value of diameter. So for this numerical, the diameter obtained is 27.194 mm. Let us now go through the second numerical. The second numerical also belongs to axial loading. A flat bar having a height of 100 mm and length 400 mm is subjected to a compressive load of 100 kilonewtons. If the allowable stress for the material of the bar is 100 Newton per mm square, determine the thickness of the bar. It is understood from this question that this time, instead of circular cross section, a rectangular cross section has been given in this numerical. Also, here the load applied is axial tensile load. Let us start the problem by writing down the given data. So this is the diagram where the load is applied. In this case, the load applied is compressive load, axial compressive load of 100 kilonewtons. So the given data is H is equal to 100 mm, height, length of the bar is 400 mm, load is 100 kilonewtons which is compressive, and directly he has given the allowable stress in this numerical as 100 Newton per mm square. Sometimes the allowable stress is also called as the maximum stress the structure can withstand as 100 Newton per mm square. We need to find thickness T of this bar. So this entire numerical, in this case, the component is subjected to axial stress with a formula sigma A is equal to F by A. Sigma A he has already given in the numerical. Load also we know it. We'll be trying to find the value of A, area, by substituting the formula of area. We'll be able to find the thickness. So sigma A is equal to F by A. Sigma A is equal to 100 Newton per mm square. will be equal to F is 100 into 10 power of 3 newtons divided by A. By substituting these values, we will be getting the value of A as 1000 mm square. By substituting the formula of A as h into T, since it is a rectangular cross section, we can be able to determine the value of T. So 1000 is equal to 100 into T. So by substituting these values, we will be getting the value of thickness as 10 mm. Let us now try solving one more numerical where the component shown in the figure is subjected to an axial tensile load. In this numerical, it has been given that the two round rods are joined by means of a knuckle joint as shown in the figure. The diagram he has already given in the numerical. We need to determine the diameter of the rod as well as the diameter of the knuckle pin. If the rod is carrying a tensile load of 50 kilonewtons and the allowable stress for the rod as well as the pin are 100 Newton per mm square in tension and 45 Newton per mm square in shear. Most important thing in solving the numericals in design is to understand the analogy behind the numericals. So in this case, the rods he was mentioning was having a diameter of capital D. This is the rod having a diameter. So he is mentioning about these two rods, rod 1 and rod 2. These two rods are connected by using a knuckle joint. In the knuckle joint, there will be a knuckle pin of diameter D. So he was mentioning about this knuckle pin. We need to find diameter of this knuckle pin also. Also, we can clearly see in this diagram in the question that a load of 50 kilonewtons has been applied. The value of F is 50 kilonewtons. It has also been mentioned that the allowable stress for the rod and the pin is 100 Newton per mm square in tension and 45 Newton per mm square in shear. So it is understood that the rod is subjected to a tensile stress of 100 Newton per mm square and the pin is subjected to a shear stress of 45 Newton per mm square. Only one thing we need to decide the pin whether it is a single direct shear stress or double direct shear stress. Let us start solving the numerical by penning down the given data. So from the problem, it is given that the load F is 50 kilonewtons. Allowable stress in the rod which is subjected to tensile stress is 100 Newton per mm square. Allowable stress in the pin is 45 Newton per mm square. We need to find the diameter of the rod capital D and the diameter of the knuckle pin small d. The type of stress in case of rod is axial stress and the related formula sigma A is equal to F by A. Let us see what kind of stress is subjected in case of pin. The pin is subjected to direct double shear stress as shown in the figure here. So the type of stress in this pin is double direct shear stress and the related formula is tau is equal to F by 2A. By using this data, we will now solve to determine the diameter of the rod as well as the knuckle pin. For the rod, as it is subjected to axial tensile stress, the formula sigma A is equal to F by A. So here F is equal to 50 kilonewtons or 50 into 10 power of 3 divided by A. Sigma A has already been given as 100 megapascals. By solving this equation, we will be able to determine the value of A as 500 mm square. Now substitute using the equation of A as pi d square by 4. Substituting the value of A in this equation, we can also determine the capital D diameter of the rod. Let us now determine the diameter of the knuckle pin. As we have already discussed that knuckle pin is subjected to double direct shear stress. Therefore, the related formula tau is equal to F by 2a. The value of allowable stress in shear is already given as 45 Newton per mm square. Therefore, 45 is equal to 50 into 10 power of 3, which is the value of force divided by 2a. By using this equation, we'll be able to find the value of area as 555.5 mm square. Now, using the formula of area as pi d square by 4, where small d corresponds to diameter of the knuckle pin, we'll be able to determine the diameter of the knuckle pin. In this case, the diameter of the knuckle pin is 26.59 mm. Let us solve one more numerical on axial loading. The link shown in the figure has a maximum normal stress of 65 megapascals. Check the design to transmit a steady tensile load of 50 kilonewtons and comment on your recommendations. He has given a link as shown in the figure. He is asking us to check the design. Check the design means to cross check whether this link can sustain this load or whether this link can withstand a stress of 65 megapascals. So in this case, we are going to find the stress once again and compare the stress with the given stress of 65 megapascals. Also, it has to be noted that this section or this link has got two cross sections, cross section AA as well as cross section BB. So this problem has to be solved for two different types of cross sections. Let us start the problem by noting down the given data. So let us start the numerical by writing the given data. We can also see the link shown. The link looks similar like a bicycle chain as shown in this figure. In this data, he has given a maximum stress as 65 megapascals, and also the link is subjected to a load of 50 kilonewtons. We need to find the stress at section AA as well as the stress at section BB. After finding the stresses, we'll be comparing the stresses with the given maximum stress, that is the 65 megapascals, and check if it is exceeding this 65 megapascals or not. To start with this, let us start understanding each section individually. The section AA is as shown in this figure. The section AA, the cross section of section AA has been given as these dimensions, where it has got a width of 20 mm and the total height of 75 mm with a hole of 40 mm. You can see the three-dimensional view of the cross section in this diagram. The three-dimensional view, if we cut the section exactly at AA, this is how we'll be able to see the diagram. Let us understand section BB. The section BB has a rectangular cross section of thickness 20 mm and height 45 mm. We'll start solving these two sections, or by considering the areas of these two sections, and we'll try to determine the maximum stress and compare the stress with the given data. Let us start solving at section AA. The section AA is subjected to axial stress. Since it is subjected to axial stress, the formula is sigma A is equal to F by A. In this case, F is 50 kilonewtons and the area is given by the cross section, which gives 75 multiplied by thickness 20 minus 40 multiplied by thickness 20. With this value, I'll be getting the value of sigma as 71.43 megapascals, which is very much high compared to given 65 megapascals. I can easily conclude here that the stress, since it is exceeding 65 megapascals, there are chances of failure of this component at section AA. Let us also check with section BB. At this section, even this section is also subjected to axial tensile stress. So by substituting the formula, sigma A is equal to F by A, where F is equal to 50 into 10 power of 3 newtons, and the area is the area of the cross-section rectangle, giving us 20 into 45 mm, we'll be getting the value of stress as 55.56 megapascals, which is very much less compared to the given data. Since the stress is very less, this link will be safe at section BP. But anyhow, let us once again discuss the summary of our findings. Stress at sigma at AA is 71.43 megapascals and stress at section BB is 55.56 megapascals. Now, since the stress is exceeding the maximum allowable stress of 65 megapascals at section AA, the link will fail at section AA. Thank you one and all for watching this video. In the next video session, we'll be discussing on determining bending stresses when the components are subjected to transverse loading. Have a nice day. Thank you.